when we're thinking about the naming of these, we sometimes consider we have the 1, 2 position. So we would say a nucleophile adds 1, 2. Sometimes we have 1, 4 addition. That means something is adding to the 1 position and the 4 position, right? So this is why we have that naming convention, because we're thinking about involving our carbonyl carbon in that reactivity. The reason why we have the alpha and beta naming position is because sometimes we're more interested in what happens at these carbons here. So we're going to learn about aldehydes and ketones that are alkyl when they can actually act as nucleophiles on these carbons, for example. And that's when we start to move into that alpha beta position terminology. All right. So it's just a good idea to know all of it, though. Okay, so unlike most functional groups, we don't have a lot of common names, but with aldehydes and ketones, we do. All right. So there are some common names I'd like people to know. So this is acetone. Use this to clean your glassware. You've probably seen this before. Probably the most common ketone that we have. We also have formaldehyde. You know, this smells really bad. We see this in biology, although I don't know if we do anymore. It's kind of toxic, but most chemicals are. We have benzaldehyde, which is a phenyl group. That's a really common name. We have acetophenone. So it's kind of like acetone, but instead of one of the methyl groups, we have a phenyl group. So that's where you get our phen from. And then we have benzophenone. Right, so people are like, oh, do I need to know the common names for the exam? You know, these are really, really common. So generally speaking, you know, we might put in, there would never be a question where like, draw the structure of benzophenone, but we might say in a short answer question, benzaldehyde reacts with sodium borohydride. And so you would need to know what benzaldehyde is from that. We try to avoid people knowing names, but things like acetone are just so common that, you know, I think it's fair on an exam to say acetone reacts with blank, and, you know, that's why it would be good to know these things. All right, so we talked a little bit about the reactivity of these on the very first day of class, but that was a while ago. So let's go ahead and think about kind of how these react. All right. Okay, so we have this aldehyde or this ketone. It's an aldehyde, of course, if R1 or R2 equals H, doesn't matter. When we're thinking about this, we're thinking about where the reactivity is. We see at the 1 position and the 2 position, this carbonyl carbon is what we're going to focus on. We see that we have a delta plus, a partial positive charge at the 2 position and a partial negative charge at the 1 position. So when we're trying to think about why this is, we know that oxygen is very electronegative, and so it's pulling electron density away from our carbonyl carbon at that 2 position, and then that renders sort of, we can draw this arrow with a positive charge at the 2 position, and the electron density is going towards the oxygen, all right? So we consider the carbonyl carbon, this here, we consider this to be electrophilic. All right, so generally speaking, react as an electrophile because that partial positive, which means that our oxygen reacts as a nucleophile, so it's a nucleophilic position. So we don't often see this react as a nucleophile, adding to very many things, but it does get protonated, and in that case, it is still acting as a nucleophile. And how we can maybe better understand this electrophilicity and nucleophilicity is by this extreme resonance structure. I'm going to call this extreme Because we don't often, if we have an opportunity to have a neutral molecule, we often do. But if you were to draw an arrow and break that carbon-oxygen double bond and put those electrons back on oxygen, our electronegative element, what we would get out at the end of the day is a negative charge on oxygen and a positive charge at the base of the carbonyl. Right, and this helps us to see a little bit more why we have the electrophilic position at the carbon and the nucleophilic position at the oxygen is because of this extreme resonance structure. Again, I said when we have two charges versus a neutral molecule, we generally prefer the neutral molecule, but this is just a way that we can sort of think about this reactivity. Now, this is kind of extreme. We don't really see this existing too much in our flask. So that means that aldehydes and ketones are not the most reactive functional group, but we have strategies to increase their electrophilicity, just like we made a lot of strong electrophiles in our first chapter of electrophilic aromatic substitution. So let's go ahead and see the strategy that we use. So we can take something like acetone. What we can do is we can protonate it. All right, so we can either add H plus to activate it, or we could add a Lewis acid. So H plus is a Bronsted acid. We could also use a Lewis acid. What would be some good Lewis acid candidates? Well, we see a lot of group 1 and 2 metals. We might add in magnesium or something like that. We might add in titanium element number 22. We might add a BF3 Lewis acid, a boron Lewis acid. So a lot of different candidates for Lewis acids here. And if we were to add a Lewis acid to this reaction, what we would get out, my goodness, is going to be a positively charged oxygen bound to our proton or our Lewis acid, right? That's why we said that's the nucleophilic position. That lone pair of electrons can go ahead, just pop over and grab our hydrogen or our Lewis acid. Bronsted or Lewis acid, doesn't matter. Now that we have this, we can see that it's a little bit more reasonable, again, to think of this more extreme resonance structure. We can return our oxygen to a neutral oxygen, and then we can place that carbon, the positive charge on the carbon. And we would do that by breaking that CO double bond and putting those electrons back onto oxygen here. And this would be our product, all right? So again, this is an extreme resonance structure, but it helps us understand why our Lewis acids are increasing the electrophilicity, right? Because now all of a sudden we have this positively charged carbon, or if you want to think of this resonance structure, we can think of it as just as more partial positive or the carbocation itself. And this helps us to understand it's more electrophilic. All right. So at the end of the day, Lewis acids or H plus, so a Bronsted acid, increase electrophilicity. At the 2 position. This is a trick we're going to use all the time. We're going to use a lot of acid catalysts. You can use this in catalytic amounts quite often. We're going to use a lot of acid catalysts with our carbonyl compounds to make them more electrophilic. All right? This is a nice way to increase that electrophilicity. Okay, so we learned quite a few reactions with aldehydes and ketones. So we're going to go for our chiming question because that is our we're going to recall which ones we've learned. So I had trouble opening it again, but let's see if I can do it. If not, it's already opened. I'm going to ask you to go ahead and put in your answers for which reactions you can recall that we've already learned. I will see if Canvas ever loads it. It's slow for me, but it is finally coming up. All right, so the question is, what reactions have we already covered? So you can go ahead and chat back and forth with your neighbors, see if you can come up with anything, and see what people come up with. We'll wait for a couple more people to respond and kind of think through what we've learned already. All right, I see people are still answering, but I know the Wi-Fi is slow, so I'm just gonna leave the question open, but let's take a look at some of the results. Okay, love it. I see a lot of reductions. We've done a lot of reductions. I see sodium borohydride, lithium borohydride popping up. We've done a lot of oxidations to make aldehydes and ketones. That's great. I see hydrides. I see organometallic reagents, Grignard reagents. These are all great suggestions. So I'll keep that open so you can keep answering. And we'll go ahead and cover some of these. All right. So that's our next learning objective. Is we're just going to recall some previous reactions with aldehydes and ketones. All right. So let's start with organometallics because those are my very favorite types of reagents. So we learned about the 4 P's of organometallic reagents. As nucleophiles with aldehydes and ketones. To make alcohols. This is back in chapter 15, on objective 15D. Clean up my handwriting there. Right, so we learned that if you have an electrophile, such as an aldehyde, or a ketone, we'll just be using an aldehyde here as our electrophile. And we react that with an organometallic reagent. For example, let's use an organomagnesium reagent as our nucleophile. Right, we learned in the first step, we have our metal carbon bond at the electrophilic position of that carbonyl carbon, the 2 position. It breaks that carbon-oxygen double bond and returns the electrons to our oxygen. Right, we haven't quenched this reaction yet, so we don't yet have an alcohol. We have a alkoxide that's negatively charged. I'll draw in our hydrogen here. I usually don't, but just so that we can see that aldehyde is still intact. We have our magnesium bromide counterion. All right, so we had a lot of challenges on the exam with the ethylene oxide opening, in which people were drawing the electron density going first to the magnesium, and then from the magnesium to the carbonyl. But we look at our byproduct, we see our magnesium is positively charged. So that means our electron density should actually be coming from the bond and going the opposite direction, right? We saw this a lot with lithium. That was what was on the exam, but the same idea. So we need to recall that this is the nucleophilic group. So you can either start the arrow from making this a carbanion or from that bond, all right? So I just want to remind everyone where we need to start our arrows from, because I'm always sad if people make the same mistake. All right, then we add in a second step, we add our H3O+, and then we end up with our alcohol at the end of the day. All right, so OH. And our phenyl group has added. All right, so we learned this before, right? This should be pretty familiar. It's kind of nice to have some review topics here. All right, doesn't have to be an organomagnesium reagent, could be organolithium, could be organosodium, doesn't have to be an aldehyde, could be a ketone, right? I'm just showing one example. All right, another thing that I saw a lot about was on the chime-in question was a lot about formation of alcohols from ketones and aldehydes. And so that's going to be our next review is the 4 Ps of the formation of alcohols from aldehydes and ketones. And this is through hydrogenation in this case. I saw a lot of hydride reagents. We'll get to that next, but let's cover hydrogenation first. So this is learning objective 16A. Okay, so we saw examples where we could take, for example, an aldehyde. We can add into our reaction H2, so hydrogen gas and some sort of metal catalyst. Palladium's one of my favorite metals, so we'll use palladium today. What we get at the end of the day is we get our alcohol formed as we've added H2 across our double bond, right, through hydrogenation. All right, so this is a nice way to make aldehydes and ketones, but we did have a question on the exam, or sorry, using aldehyde and ketones to make alcohols and reduce double bonds. We also had a question on the exam about some chemoselectivity. So you need to recall that H2 and a metal catalyst also reduces CC double bonds. So if you have an alkene, this is going to reduce that as well. In this case, we don't have to worry about that. We don't have an alkene, but I'm just going to remind you of some of the key things that we've learned about our reduction conditions and when we should be using certain reduction conditions versus not. All right, I saw a lot of hydride reagents on our chime-in question, so I like to see that. So we learned about the 4 Ps of formation of alcohols. And again, this is still from aldehydes and ketones. And instead of through hydrogenation, this is through hydride reagents. We learn this as learning objective 16B. Okay, let's start with benzophenone. You'll recall that is a ketone with 2 phenyl groups on it. And we learned that you can use a hydride reagent such as sodium borohydride. And an alcoholic solvent, I'll just use ethanol as an example, but it could be any alcohol. We could use isopropanol, we could use methanol, tert-butanol if we were going to heat it, any alcohol. All right, and then we noticed that we know about the electrophilic and nucleophilic site here, all right? And we know that the electrophilic site is the 2 position, the carbonyl-carbon, and we know that our hydride is coming from our sodium borohydride reagent. We know the nucleophilic position needs to be matched with a proton, and that proton is coming from our alcohol as H+, all right? So on the exam, we had a lot of people that were really uncomfortable with a hydride versus a proton, all right? So this is the structure of sodium borohydride, all right, with our sodium plus counterion. What we're looking at here is we are looking at this negatively charged compound or the borohydride is negatively charged, and we see that our delta minus is on the H's. So that negatively charged overall counterion, that minus charge overall is distributed across the 4 hydrides, meaning that these are nucleophilic hydrides. All right, we saw a lot of people reducing ketones with sulfuric acid, which is H+. So a hydride is essentially H-. It's a nucleophile, right? So again, I don't want people to make those mistakes again. We also learned some other conditions as well. You'll recall we learned lithium aluminum hydride in one step, and then we said that you could add in water in a second step. We did need to be careful because these conditions also reduce carboxylic acids. That was on the exam, right? So we do need to be very careful when we're choosing our reducing agent. Do we have an alkene? We probably shouldn't hydrogenate. Do we have a carboxylic acid? We should probably use sodium borohydride. If we have none of those things, you can use whatever of these reagents you want. All right, we also learned more reduction chemistry actually very early on, but we didn't really connect it to the aldehyde and ketone functional group, right? So we learned about the 2 P's for reduction of ketones to CH2s. We learned this back when we were talking about Friedel-Crafts acylation, which is also known as electrophilic aromatic substitution for acylation, all right? So this was back all the way, one of our first chapters, actually our first chapter, learning objective 13I and J. We only use this in the context of reducing off those acyl products to generate alkyl products, but we can really use this reduction anytime. So here we could take something that looks like this. We could have made it through electrophilic aromatic substitution or some other method. It doesn't really matter. We have acidic conditions. All right, and our acidic conditions were our Clemmensen reduction, where we use zinc, mercury amalgam, and HCl. And we reduced off that ketone to a CH2 group, a methylene. All right, we call these Clemmensen reductions. Right, doesn't matter how you made that ketone. You can always reduce that ketone using these conditions. It doesn't have to be through electrophilic aromatic substitution chemistry. We also learned in this chapter, we learned basic conditions. Also, this is another 2P. These mechanisms are just beyond the scope of this class. You need a little more understanding of some radical single electron chemistry. So we're not going to worry about that in this class. All right. And what we used there was hydrazine, which is H4N2, or this is how it's actually connected. We needed a base in this, so under basic conditions, and then alcohol solvent. We get to the exact same product, right? On Wednesday's lecture, we're going to understand why it's so important to have some things run under basic conditions and some things run under acidic conditions. It's because we have other functional groups that can be sensitive to those. And we called these the Wolff-Kishner reduction conditions. All right, so we learned both these. Again, doesn't matter if we made this through EAS or we made it some other way. As long as we have this ketone here, we can reduce it down. All right, so those are the aldehyde and ketone reactions that we've already learned. So a little bit of a recall lecture for you. The next learning objective should be that as well. As we're going to take a look at the stereochemistry implications of additions of nucleophiles. All right, so this is learning objective 18C. We're going to identify if stereoisomers are formed. All right, and specifically if they're formed upon nucleophilic addition to carbonyls. In this case, we're of course learning about aldehydes and ketones specifically, but this can be used for any carbonyl. All right, this is chapter 1813. Okay, so we learned a lot about stereochemistry over the last couple of days. So let's go ahead and see what we're thinking here. So we have acetone here as an example. Let's see if we can identify whether this is going to form stereoisomers. So let's add in a nucleophile. Depending on the nucleophile, we might need to quench it. So I'll just say H+ source. All right, so now we need to see if we add a nucleophile here, what happens. So we're gonna form an alcohol with our H+ source, and we're gonna have a nucleophile that's now bound to that carbon. Okay, when we're taking a look at this molecule and we're trying to determine if acetone is going to give us stereoisomers of anything, stereoisomers and chiral molecules have to have different groups bound to that carbon. And when we take a look here, these are the same group, right? Those are the same group. So this is not a chiral molecule. We do not have another enantiomer anywhere to find, all right? Those are the same group. Okay, so now let's try on a different molecule and see if we can identify, knowing that we have to have a chiral molecule at the end, if we have different groups. Let's start out with acetophenone. So acetophenone has a methyl group and a phenyl group on it. Now let's say a nucleophile is added. All right, I'm going to say there's a caveat with this nucleophile. I'm just going to say, in this case, not methyl or phenyl, because that would give us the same group that we already have, right? So in this particular case, we'll just have that caveat. And we'll add in an H+ source. Okay, so now we're starting out with something that has two different groups. We have group A and we have group B. We have group C, which is going to be our oxygen, and our nucleophile is going to be group D. Because we said that's not methyl or phenyl, these all are going to be different groups, and we are going to get two enantiomers out of this reaction. So we can first have our oxygen as a wedge coming out. And then our nucleophile, we can say, perhaps added from the back face. And so now it is a dashed bond. And now we also need to say, what if our nucleophile attacked, instead of the back face, it came from the front face? We would get the other enantiomer. It would push the alcohol backwards. And then our nucleophile would be coming towards us. All right. All right, so we have two enantiomers. In a 50-50 mix. All right, so our aldehyde, we could call it this aldehyde, or sorry, this ketone, something we could say it's prochiral, meaning that it has the ability to generate two chiral molecules, right? So these are two enantiomers of a chiral molecule, all right? So we just need to be able to look and identify. So on an exam, if we took a look at this, we say there are two groups here. We check our nucleophile isn't one of those two groups. Right. We can go ahead and say that we're going to get a chiral molecule out. And then we would say plus enantiomer for two enantiomers. We often see people just adding stereochemistry arbitrarily all over. So this first reaction, they would draw this and say plus enantiomer. But there is no enantiomer of this because these are the same group, all right? So I want you all to be able to sort of take a look at the stereochemistry and say, okay, does my electrophilic component have different groups? And is my nucleophilic component also have different groups, all right? So that's going to help us start to understand if we form chiral molecules and we need to say plus enantiomer. All right, so thus far, everything you've seen before is actually something that you've seen before, all right? So this chapter and some of these intermediates, the mechanisms, I'm going to be real with you all, can be quite complicated. There's a lot of arrows that we need to draw. There's a lot of different intermediates. And so to get on the same page before we start to draw up those mechanisms, I'm going to introduce you to some completely different functional groups and the names of them that we're really quite unfamiliar with. And this means that we will be able to move through the mechanisms more informed and more easily because we know what these intermediates are. So I'm going to say, okay, this hemiacetal goes to a cyclic acetal, or this ketamine goes to a hemiaminal, and those are going to be things that you're going to be able to track when I'm talking about the mechanism. So I'm going to introduce you to some functional group names. All right, so our learning objective 18D is to describe the functional groups formed from reactions of aldehydes and ketones. All right. So because aldehydes and ketones are a little bit different, we can't always have the same functional group formed from both of them, but the names will be relatively similar to each other, all right? Okay, so we will start out with our arbitrary ketone. I'll just put R1 and R2. Those are carbon-based groups, we know. If we have an aldehyde, I'll just say R1 and H. All right, so I told you in the beginning that sometimes we use things like ket or -one when we're talking about ketones in some of these names. Sometimes we use al. Sometimes we use other abbreviations, all right? So some of these names are not necessarily going to make the most sense in the world, but that's why we're learning them. Okay, so if we were to react water with a ketone, what we would get out at the end of the day is going to be called a hydrate. All right, a hydrate. Or sometimes we call this a gem, meaning geminal, meaning that it's on the same carbon, diol. Di meaning two, all meaning alcohol. So I will refer to this either as a hydrate or a gem diol. All right, if we add, which we will do, this is what we have happens when we add water, right? That's why we call it a hydrate. We've hydrated this, we've added water to it. So when you're thinking about like staying hydrated by drinking water, like it's derived from chemistry terms. Okay, so if we add cyanide instead to a ketone, we're going to get out a cyanohydrin. Cyanohydrin. All right, we're going to learn the 4 P's of this. We're going to learn the mechanism. We're going to learn, I think, 3 sets of conditions, if I'm recalling correctly, how we can make this with this cyanide group. Sometimes we call this a nitrile group. Sometimes we call this a cyanide group. So we call this intermediate a cyanohydrin. All right, so if we have specifically an aldehyde here and we add a alcohol to it, what we get out at the end of the day is called a hemiacetal. All right. So the acetal portion is coming from an aldehyde and adding an alcohol. Hemi means like kind of like halfway, because we could also form from an aldehyde with two equivalents of an alcohol, not a hemiacetal, but just an acetal. All right, so hemi means like halfway, like hemisphere. And when we go all the way and react this fully to as far as it can react, we get an acetal. All right, so if we do this with a ketone, we get a ketal. All right, it's kind of confusing because the word al is in there and we think of aldehydes, but it's not referring to that part of the functional group. The ket is the part that we're referring to. All right, specifically, we're going to learn a lot about protecting groups very shortly. And so we often have cyclic acetals, meaning that the acetals are not from two separate alcohols. It's from a diol. We call this a cyclic acetal. Oh, sorry, a cyclic ketal. The cyclic acetal would not be from a ketone, it would be from an aldehyde, right? So this is not an exhaustive list of names. Turns out that there's even more, right? The reason why I'm giving you these, we don't usually go over names, is that we're going to need them for our mechanisms. So this is what happens when we react aldehydes and ketones with oxygen and carbon. Yeah, question? We can form a hemiketal. Excellent. Yeah. So a hemiketal would be the equivalent of a hemiacetal, but R1 and H would be R1 and R2. So yeah, a lot of these can be like sort of you can extrapolate to the other names. So yeah, great question. Okay, now what happens if we add amines? These are just alcohol nucleophiles. Amines are even better nucleophiles. These names get even more kind of crazy, all right? Well, not crazy, but they're more unfamiliar to us. Okay, so if we add an amine to an aldehyde, then we get a hemiaminal. Hemi, so halfway. Aminal is because we have an amine. If you try to type that out, your phone will autocorrect that to animal. It's not what I'm writing. It's aminal. All right. So if we want to take this a step further, we don't actually get an aminal version of our ketal. We get something else. We end up getting an imine. So an imine, not an amine. An imine has a double bond to our nitrogen. So we could specifically call this an aldamine for it being derived from an aldehyde, but sometimes for no reason at all, chemists like just didn't pick things up. So generally speaking, people still just call this an imine in the lab, but it's technically called an aldamine. The reason I pointed that out is you can get ketamine, which is in fact the name of a functional group. That's what it was first, a ketamine. Is the ketone version of an amine. Right? This is actually what ketamine means. All right. So that's another group we're going to learn about how to make. And then the final group that we're going to learn how to make in this class, not including all the things that we're going to extrapolate on, is going to be called an enamine. So I'm drawing NR2 here because you have to have two groups on there. Otherwise, you go to the ketamine. This is called an enamine. You will hear other chemists. This is a name that we debate about how to say this. There's not a convention. I like calling it an enamine because it has an alkene, so I associated that with ene, like we would say hexene or something like that. And amine refers to the amine. You will also hear people call this enamine, all right? But you will hear me refer to it as enamine, but your TAs may call it an enamine because that's kind of how it looks like it's spelled. It's the same thing, but I like to understand that it has an alkene, so ene, and then the amine. All right, so brush up on these so that when we get into the mechanisms and they go really fast, we have a much better foundation than if we didn't know these names.